We're going to pick up where we left off from the risk identification function and take a look at Requs AI Optima. The Requs AI Optima can and does identify development factors that you could be potentially overkilling. In my example, I've got a percentile rank that's very, very small. And so it's possible that we could get by with fewer development practices than what we actually have. So let's take a look at the overkill analysis. You can see, let's look here. It's already telling us that several of our categories look like they might be overpopulated with development practices. And we don't have really any gaps in any of the categories. So this particular project might be ripe for removing some overkill. We could see our initial defect density is 0.0307, which is quite low, the prediction. We can sort the list of practices that we're currently implementing. So the overkill checker shows what practices we have said we are doing. And it shows the relative impact. You can see 1 is low, 4 is high. So these are in order of generally the lowest impact, biggest amount of calendar time, and also cost. Calendar time and cost can be two different things. In that calendar time, many times is not more costly, it's a culture change. Many times changing a culture takes time, but not so much money. Cost would be things like we have to buy tools, it's very exhaustive, we need more people to do the task. It's possible to have practices that take short amount of calendar time but high cost. So these two are not necessarily the same. But we see the ranked order by defect density. So the goal here is to see if by clicking some of these items here, if we can notice some that really have almost no effect or even possibly a negative effect on defect density. One that I see right off the bat is tracing coding functions back to a software requirement. That can be exhaustive. Let's click that and see what happens. Okay, getting rid of it actually helped. It reduced the defect density by a very tiny amount. Let's look at the next one. All software requirements are traced to at least one function. It's the reverse. Again, we're seeing that the defect density is actually a tiny bit less. Let's pick another one. Let's see. How about code completion metrics? Let's click that one. That sounds like that could be kind of expensive. Again, we see almost no effect on defect density. There could be other reasons to have these development factors, but if most of the reason is to reduce defects, then maybe we have too many of these factors. Let's look at naming conventions in the coding standard. Getting rid of that actually caused the defect density to go up a little bit, so let's put that one back in there. But right now, we have a few things. These are fairly, it's not that they're exhaustive, but they take a little bit of work, and they had actually no real effect on the defect density. Now, if we keep these at yellow, that means we have turned them off. Instead of saying yes in the survey, we're saying no. We can unclick them and just discuss this with management, or we can commit to reducing them and leaving them out of the prediction. That's the way it works. But right now, when they're shaded yellow, that means we have checked them no in the survey, which means we're not going to do them. All right, I'll click them back. Okay, so let's now go to gap analysis. We actually have no gaps for this particular project because, well, I guess we do have a few gaps. Not many, not too many here. So the gap analysis are the things that we said no to that maybe saying yes to could give us some value. And again, they're in reverse order. Now, these are in order of highest impact, whereas the overkill practices were lowest impact. You can see relative cost, relative time. We can sort them any way we want, by the cheapest, the shortest to implement, or by the biggest effect on defect density. So let's look at one of these that looks like it'd be the cheapest to implement. Okay, there is a schedule for software corrective actions, which means they aren't fixed in an ad hoc fashion. That doesn't sound very expensive, so let's click that and see what happens. Not much. Okay. Let's see. The design is in writing as opposed to verbally communicated. Let's click that. Okay, that didn't have much effect. It's explicitly part of the software engineering schedule. Not much effect there. There's a written interface design. Let's see what that does. That actually made things worse. Okay. Oh, here we go. Actually, having the design in writing, oops. Okay, having the design actually in writing reduced the defect density there down to 0.0297. So that one actually did have value. We can go through the rest of these. We don't have many of these. The problem here is that we have so many other development practices that whatever we click here is probably not going to have much of an effect. But you could see the idea that the gap analysis is the exact opposite of the overkill analysis. If we make room for the gaps by removing the overkill, they'll have more effect. Okay, once we've looked at the overkill and the gap analysis, let's look at the interactive analysis. And with the interactive analysis, I'm going to show how this works. The cycle time and the effective size work together. So right now we have cycle time set at 12 months, which is really, really big. Let's set this down to more of an agile development at quarterly. Now, if we're going to reduce the release cycle down to 1/4, we also have to change the effective size down too. Otherwise, we'll have massive pileup in defects. So right now, I reduced the cycle time by 1/4 and also the amount of stuff in each of the program increments. And you can see the initial analysis and the escape defects, we're really having the same amount. We just have more releases. One thing we wouldn't want to do is reduce the cycle time but hold the scope constant. If we did that, we could see we'd have defects here increasing. There's a big difference between this and this. All right, so that's one analysis we can do. One of the more important ones we can do is to look at this bar over here to the right. Right now, the bar is way to the right of the defects because I have a program where we've overkilled the development factors. But let's go ahead and see how sensitive that is to defect density. Okay, we'll move it up. Not that we want to make the defect density worse, but let's see the sensitivity analysis. So somewhere around 0.2 defect density, you can see the bar has moved to the left, which means we'll have more technical debt. We can move it up a little farther. Oh, here we go. The bar is even farther to the left now. If we keep going, oh, now the bar is almost at the top, which means we're deploying almost as many defects as what we're seeing in testing, which is never super good. If we keep going, oh, now the bar is actually at the very top of the mountain, and that's where it stays. So we can see the effect of the predicted defect density itself on the shift to the left goals that we have. All right, so now let's look at some of the other features that affect this pie chart over here. The pie chart shows the percentage of defects fixed. We can move the sliders for the corrective action hours we have available in operation. And we can see if we want to fix all the defects in operation, what we would need for time is right around, really, because we have so few defects, we only need about 30 or 40 hours of corrective action time, assuming that it's 8 hours per corrective action. And then we could move our slider for corrective action per cycle. So the corrective actions per cycle is showing us how much time we have to fix the defects that are found in testing. So if we move the slider, we can see right around 180 hours is about what we would need to fix all of them found in testing. And we can see the test hours per cycle here and the effect that that has. Oh, we can see that affects our interactive escape defects up here. Okay, notice how it had an effect here on the interactive escape defects because we're finding more of them as we get into development. So in summary, the interactive analysis actually allows you to see the sensitivity of the key inputs and also to balance them out.